So we're beginning today by kind of just, if we go back to where we were Friday. So Friday we started to look at the concept of dilutions. We were looking at overall concentration kinds of things, looking at calculating concentrations from kind of material. And then we talked about the idea of a dilution, where instead of starting from solid and water to make a solution, what if we already had a standardized solution? What if we already had a solution where we knew its concentration and we just wanted to make a solution that had a lesser concentration? And this kind of thing happens all the time. When we get hydrochloric acid from the manufacturer, it comes to us in a 12 molar quantity, concentrated acid. But you know as well as I do, most of the time when we are working with hydrochloric acid in the lab, it's not the 12 molar variety. It might be 1 molar. It might be 0.1 molar. It might be 6 molar. How do I go from that high concentration to the concentration that we're actually going to use? The answer there is dilution. And with dilution, remember what we ultimately are banking on as far as this goes is the idea that when we pull that subsample out of this solution, the number of moles of that subsample do not change regardless of how much water we add to this. So if I take half of this out and dilute it to 100 milliliters, that's great. The number of moles didn't change. If I dilute it to 600 milliliters, the number of moles didn't change. If I dilute it to 2 liters, the number of moles didn't change. All that changed was the total volume. And so what the dilution equation allows us to do then is it allows us to look at this from a scenario standpoint and say, since our number of moles are even, then the concentration values don't really matter in terms of what that concentration unit is. What matters is that we keep the concentration unit consistent. So I could have molarity on each side. I could have percent by mass on each side. I could have parts per million on each side. It wouldn't matter. So long as the unit is the same on each side, I'm banking on the concept of the number of moles being equal. And same thing for the volume. For the volumetric calculation, it doesn't matter if I have milliliters or liters or any other unit. So long as the two units are the same, ultimately they will cancel out in this calculation if we need them to cancel out. And what that allows us to do is it allows us to take some shortcuts, some liberties here, where if I don't have molarity, it's okay. I don't need to convert everything to molarity first to use this equation. And similarly, if I have milliliters instead of liters, great, who cares? So long as I have the same unit on the both sides, the equation will work just fine. So let's take a look at an example problem that deals with this. And the sample problem is this. I've got intravenous saline solution that I'm interested in making. We call that physiological saline or normal saline. It's set at a concentration of 0.155 molar sodium chloride. Now, this is the kind of saline solution that would be put into a saline bag. And let's say that you went to the hospital to get fluids because you're dehydrated. This would be the stuff that they would give you. They wouldn't give you pure water because your blood system is not pure water. It's mostly water, but there's a lot of ionic components to it as well. And if you put just pure water in there, it actually does more damage to your body than it does help it. Now, let's say that in this particular scenario, I need a certain amount of normal saline, but I don't have any on the shelf. Instead, I have a 1.5 molar saline solution that came to me from the manufacturer. If I needed to make 10 liters of physiological saline, how would I go about doing it? Well, that's where this equation comes in handy, because what I can look at here is I can say, okay, the physiological saline, that's the stuff I'm trying to dilute to. So there's my V2. And this is the concentration I want it to be. So that's C2. Here's my stock solution. It's at 1.5 molar. So that's the original concentration. I'm trying to figure out the volume of standard solution. That would be my V1. So now that I have all the values, now it just becomes a matter of plugging them in. 1.5 molar sodium chloride times V1, because we don't know how much we're going to need, is equal to 0.155 molar sodium chloride, the normal saline, and we want 10 liters of this stuff. Well, this equation sets up pretty easy to be solved. I need to get V1 by itself, so I'm going to divide each side by 1.5 molar. And when I do that, on the left-hand side, everything cancels out except for V1. And on the right-hand side, only the concentration units cancel. I'm left with liters. And so I do the calculations here. 0.155 times 10.0 divide by 1.5 to 3 significant figures will give me 1.03 liters of the stock saline solution. So how would I go about making this particular amount? Well, I would need to go to my standard solution, measure out my 1.03 liters of that stock using a graduated cylinder or some other kind. And then I would dilute that up to 10 liters using a volumetric flask or a really, really large graduated cylinder or something similar. What I have to remember is that the 10 liters here doesn't refer to the amount of water that I add. It refers to the total solution at the end. So roughly speaking, we would add about 9 liters of water to this stock solution that we measured out to give us a total of 10 liters in full. All right, any questions about dilutions or the dilution equation here? So I'm going to talk about titrations next, because titrations are probably the most common application of these kinds of reactions in solution. You did a titration last week. In a titration, what we are doing is we are taking a solution whose concentration we know very, very, very well, and reacting it with a solution whose concentration we do not know so well in order to find the concentration of that other thing. Now, couple of terms that get thrown about here. The solution that is in the burette, the one that we know, is referred to as the titrant. The solution that we don't know the concentration of, the one that we're trying to find, we call that the analyte. Now, the problem with titrations that we always run into, even though we generally get really good results with titrations in terms of our glassware is usually very precise. So we usually get a minimum of 2 decimal places. And depending upon the amount of analyte, the amount of titrate that we use, we get anywhere between 3 and 4 significant figures with each one of our measurements. So that's pretty precise stuff when we are looking at this kind of broadly. The problem we run into is this. Sulfuric acid, any acid for that matter, clear and colorless. Most bases, clear and colorless. The products of their reactions, most of the time, we usually have water, which we know is clear and colorless, and we have some sort of dissolved salt that is also, you guessed it, clear and colorless. Now, we talked about this to some degree when we were talking about ionic equations. How do we know that a reaction did occur? Well, we were able to prove that through our use of solubility rules, our understanding of electrolytes. We can prove that this reaction actually does happen. But in terms of the titration process itself, how do I figure out the concentration of the analyte if I don't know when the reaction is actually over? That's a different kind of problem entirely. And the problem gets solved in a lot of ways through the use of indicators. So next to this analyte here, this little vial here contains an indicator. Indicators help us to determine what is called the end point of a reaction. And they do so by the fact that they turn color based upon a change in pH. Now, that's not the true stoichiometric equivalence point. So ultimately what we're trying to do in an ideal situation with a titration, we're trying to figure out what is called the equivalence point. The equivalence point would be, I know exactly how much of the analyte is there, how much titrant goes in there until I get an exact amount of base. So the amount of acid and the amount of base have equalized each other. That's my equivalence point. At the equivalence point, both of these have reacted fully. There is no leftover. There is no excess reactant. Everything is behaving as if it were the limiting reactant. There's nothing left over from a reactant standpoint. That's the ideal situation of a titration. Problem with that is that it's incredibly hard to detect, which is why we use indicators and why we search for endpoints to try to help us estimate what that equivalence point is. Now, the good news for us is that if we use the proper indicator, those indicators are actually pretty reactive and can do a really good job of honing in on that equivalence point. So if I choose a good indicator, one that changes color around the time where that equivalence point would be reached, they can be accurate within about 1/10 of a milliliter. Now, if that doesn't sound good to you, remember what your standard was for the experiment. You had to get all of your readings within a 0.2 of a milliliter window. in order to take the average to figure out what the concentration was. That was a 2/10 window. The indicator specificity is only 1/10 of a milliliter. So it is more precise than we were asking you to be in the lab. So it does a pretty good job if we choose the right indicator. Now, there are a lot of different indicators that exist. The one we used in lab was phenolphthalein. We see this pH change happening around pH 8, which is actually pretty close to where we would want it to be. And we get this colorless solution turning pink in the presence of base. For titrations that don't have that particular pH range, there are others that exist. Methyl red is one example, Congo blue, bromocresol green, bromothymol blue. There are a lot of different versions. They're all dyes. They're all pH specific and will change colors when that pH falls from one range to another. So in the case of phenolphthalein, up until pH 8, it stays colorless. Beyond pH 8, it turns this hot pink kind of color. And the intensity of that color increases as you get further and further away from pH 8. So we move on from titrations, which have this very kind of specific purpose. They have a very set procedure in terms of what we do. Let's talk about things a little bit more broadly here. What if we are dealing with solutions? What are we dealing with chemical reactions that involve solutions and trying to figure out certain kinds of things about their reactions? Like trying to figure out how much product I'm going to get from this given solution. Or working backwards, if I use this much of a solution, how much of a particular metal was in a given starting material. Those are kinds of things that we can do inside of the framework of stoichiometry. Now, the problem we run into is that our conventional framework of stoichiometry did not include anything having to deal with solutions. If we go back to module 4, all we had to work off of were the idea of looking at grams and particles and moles. The problem that we run into with solutions is that particles don't make any sense inside of a solution. No easy way to count them. Grams don't make a whole lot of sense inside of a solution because we're usually interested in the solute, but the majority of the mass of the solution is water. And so we'd have really no good way of linking those two ideas together very easily. But we do have something that we can work with, and that is molarity. Remember, molarity is moles of a solute divided by liters of solution. Well, if I know the volume of my solution, I can convert that volume into moles by simply multiplying that volume in liters by the molarity. And if I did that, liters would cancel, I'd have moles. And now that I have moles, I'm in business. I can follow the exact same kind of procedures, the exact same kind of protocols that I did in module 4, where I just take my moles, use the balanced chemical equation to convert it to something else, and then take it from there. Maybe I want to go from moles of one thing to another volume. I need to figure out the molarity. Maybe I want to take that moles of something else and turn it into grams. I can do that with molar mass. The possibilities are kind of endless here. The only thing that we were missing was the link to get us to moles. And that link is the molarity. So in solution stoichiometry, there isn't really anything that is new here. What it is we're taking two concepts that we knew beforehand, the idea of molarity and the idea of stoichiometry, and now we are fusing them together by using molarity to connect moles and volume. So let's take a look at an example here. What is the volume of a 0.225 molar magnesium chloride solution that needs to be added to 37.5 milliliters of 0.250 molar silver nitrate in order to precipitate all of the silver 1 ions? Okay, there's a whole lot of junk in that problem here. Let's try to break it down to what is actually being asked of us. First of all, we have our starting goods. We have our volume of silver nitrate, and we have its concentration. What we're trying to figure out is the volume of a different substance. Now, coming back to our mole map here, if we're trying to organize ourselves, we're starting here. We know the volume of a solution and its molarity. So we can use those two things together to figure out the number of moles of the silver nitrate. And from there, we can go from moles to moles. And since it's asking us for final volume, we can go from moles of the magnesium chloride to volume using the molarity there. So what we have here is, again, using this as a organizational system, we can see how to connect the information that we're trying to piece together. Now it just becomes a matter of organization and connecting the dots. So we want to go from liters of silver nitrate solution to moles of silver nitrate to moles of magnesium chloride to liters of magnesium chloride solution. That's the path that we're going to follow. How do we connect all of those dots? Well, again, that's where the mole map kind of helps us out here. First thing we need to do, we need liters of solution. Right now we have milliliters. So dividing this by 1,000, we would get 0.0375 liters. So that's where we're going to start. 0.0375 liters of silver nitrate solution. And the first thing that we want to do is we want to convert that into moles. Here's where that definition of molarity helps us. Molarity would be moles of silver nitrate per liter of solution. So I've got 0.250 molar, so that would be 0.250 moles in every 1 liter. My liters of solution cancel. Now I have moles of silver nitrate. My next step is to convert the moles of silver nitrate into moles of magnesium chloride. So moles of silver nitrate to moles of magnesium chloride. Here I'm following the balanced chemical equation. 1 magnesium chloride for 2 silver nitrates. My moles of silver nitrate cancel. My last step is to convert the moles of magnesium chloride into liters of magnesium chloride solution. Here again is where molarity is coming in. Molarity tells us that there is 0.225 moles in every liter of solution. So my moles cancel. I'm left with liters of solution. 0.0375 times 0.25 divided by 2 divided by 0.225 to 3 significant figures, we would get 0.0208 liters, which would be 20.8 milliliters of the magnesium chloride solution. So yes, there's a lot going on with this problem. This is where solution stoichiometry can be really kind of difficult for us because it feels like we're being asked to pull a lot of different pieces of information in at the same time. Luckily for us, though, the way that I've just shown you how to do this is actually considered the hard way. If you remember when I started talking about this information here at the beginning, I said there are going to be circumstances where a shortcut can be used. And here's where that shortcut comes in. So you used this equation last week. This is what we call conventionally the titration equation. The idea that if I have a titration, because I'm dealing with solutions on both sides, because I'm looking at moles of sodium hydroxide turning into moles of sulfuric acid or moles of oxalic acid or whatever it is, this equation can be used as a shortcut to doing the actual stoichiometric work. And it works because it takes into consideration all of the calculations that you would have had to do along the way. Now, here's the beauty of this particular equation. We can actually modify it, and we can modify it to our needs based upon a really simple idea. If the whole idea is premised on kind of the same idea that the dilution equation is, in that we are equalizing our number of moles, and the way that we do that in this case is by that stoichiometric coefficient in the denominator. That's the only difference between this and the dilution equation, is the fact that this has that stoichiometry in the denominator there. If we take that kind of convention into consideration, if I know the concentrations and the volumes of each of my things, I can use those to solve for each other. And so what I want us to do is, if I just look very quickly in context here, and so we have to move these around just slightly so that we can see everything. This was the calculation that we did here on the bottom to get to our answer of 20.8 milliliters. If we do that same calculation using our values here, using our stoichiometry, and let's just, for the sake of argument, we're going to make all of the ones the silver nitrate and all of the twos the magnesium chloride. Look how cleanly this comes out. The molarity of the silver nitrate was 0.250 molar. We had 37.5 milliliters of it. The stoichiometric coefficient for the silver was 2. On the magnesium side, we knew that the concentration was 0.225 molar. We didn't know the volume. Its coefficient was 1. To get V2 by itself, I would have had to divide each side by 0.225 molar. So just doing that real quick. All that cancels out. The molarities cancel out. What does my calculation look like? I'm multiplying 0.250 by 37.5. If I go to the stoichiometry, I multiply 0.250 by 37.5. And I'm dividing by 2 and 0.225. And here in the stoichiometry, I divide by 2 and 0.225. The net result is I'm going to get the same answer, 20.8 milliliters. Why does this work? Because again, the whole point of this titration equation is to simplify the overall calculation. Since I'm going from solution on one side to solution on the other side, I know I'm going to have molarities involved in both. I know I'm going to have volumes involved in both. The only thing that I'm missing is the balanced chemical equation, the stoichiometry part of it. So if I have that, I'm set. I can use the titration equation for any situation that goes from solution to solution. Any situation that goes from solution to solution. So it doesn't have to be just acid-base. It doesn't even have to be a titration. It can just be a matter of, if I dump this solution into this one, how much of each do I need? That makes the process a lot simpler. Now, there are still going to be scenarios where you need to do the actual stoichiometry. This is an example of one. How do I know that it's an example of one? Even though it says that this is a titration, the key term here I'm being asked to convert to a mass. I can't convert to a mass using solutions, using molarity. I mean, I could, but it would take way more steps than are necessary. In this kind of situation, what I need to do is a more traditional stoichiometry. So I need to turn my liters of permanganate solution into moles. turn my moles of permanganate into moles of iron, turn my moles of iron into grams, and then since it's asking for grams, turn those grams into milligrams. Now the process there, pretty similar to what we did in the first example without the titration equation. I'm going to start with my volume, which I need to convert to liters. That's the other advantage. If I know I'm solution to solution, if I can use the titration equation, I don't have to convert the milliliters into liters first because they'll cancel out anyway. But here I have to. 0.03912 liters of permanganate solution. First step, I need to turn the liters of solution into moles. For that, I need the molarity. So 0.00250. My liters cancel. Second step, I need to turn the moles into moles of iron. So moles of permanganate into moles of iron. That ratio here, 1 permanganate to every 5 of iron. So my moles cancel. Now I'm going to turn the moles of iron into grams. For that, I need the molar mass. Molar mass of iron is 55.85 grams per mole. My moles of iron cancel. Last, I want to turn the grams into milligrams. 1 gram is 1,000 milligrams. Now, why did we do that last step? Why is it asking for milligrams? It comes down to the numbers. My volume is small. My molarity is small. Chances are pretty good the number of grams, the number of moles of iron are small as well. Turning it to milligrams just makes the number a little bit more manageable. 0.03912 multiply by 0.0025 multiplied by 5 multiplied by 55.85 multiplied by 1,000 to 3 significant figures because there are only 3 in this molarity. It's 22.3 milligrams of iron. So if you were in a pinch, if you're given a problem that requires you to convert to mass, or requires you to convert a mass to a solution, then you have to use the stoichiometric technique. You have to go through it and follow kind of the boxes piece by piece by piece by piece. But if you are given a solution to solution kind of problem, then that other equation really is a lifeline for you. It makes the calculation so much easier because you just have to solve for what's missing. That turns kind of nasty dimensional analysis into a much easier to convert algebra problem. But you have to do it under the right conditions. Right. Any questions with this? All right, one last thing before we get to the go home for today. This is an easier one by comparison. This is just a simple straight up titration. I want you to try it here. You've got a couple of minutes to do so. If I have 30.34 milliliters of a 0.135 molar solution of hydrochloric acid, neutralizing 25 milliliters of sodium hydroxide, what is that molarity? Most important thing that you have to pull out of this is before you do any kind of calculation, you need to make sure you've got the equation and you need to make sure that it is balanced. If you don't do that, you haven't done a titration. You've done a dilution. And if the solution is not a one-to-one solution, you're wrong. And there's no way to get it right until you have that balanced equation. Now, luckily for us, this one's already balanced. Now it's just a matter of, can we put in the correct values in the correct places? So there are two ways to do this one, just depending upon what you set up as your ones versus your twos. I chose hydrochloric acid as my ones. And so if you do that, you'll set it up. M2 is being what you're solving for, since that's what you don't know. And then algebraically, all you have to do is just divide each side by 25. And that would give you the answer here, which should be 0.164 molar. Now, the assignment that is due tomorrow night has kind of a good blend of both of these types of problems. I want you to kind of get used to being able to do this both ways, not just a titration, but also can you extend it to stoichiometry beyond titrations. But that is the end of this particular module for us. So make sure that you do answer this last question before you leave. And then if you do have any questions about the homework assignment that is due tomorrow night, please feel free to reach out to me between now and then. On Friday, we will start up with module 6 after this solubility proficiency. Have a great day.